Okay, let's try this one more time. All right, this is a Careers in Tech summer series with DVP speaker David Bader, and he will be speaking. He has a very interesting topic for us tonight. And without further ado, I'm going to go ahead and pass it over to our speaker for tonight.
Thank you, Michael, for that nice introduction. And hopefully you can all see my screen now. I'm really glad for the invitation to speak here and also seeing quite a number of friends on this session. My talk today is on solving global grand challenges with high-performance data analytics. And I'll tell you a little bit more about these areas as I go through the talk. But I'm very, very excited about giving this talk tonight and talking about some of the motivations for solving some of the largest data analytic problems in the world. So I'm currently a distinguished professor at the New Jersey Institute of Technology, where I also am the founding director of our Institute for Data Science. And this talk is part of the IEEE Computer Society's Distinguished Visitor Program, and I'm pleased to be speaking on that behalf. So let me tell you a little bit more about the areas that I've been working on and also about some of my past history. So in 2021, I received the IEEE's Sidney Fernbach Award for developing the first Linux-based commodity supercomputer that has become the model for all supercomputing today. So this was quite a test of time for a system that I developed around 1998. Again, the first supercomputer that used commodity parts and Linux. Here's a picture of that machine on the upper right. And this machine was deployed at the University of New Mexico using Intel processors and a few components. But the real key to this machine was it was the first one allocated to National Science Foundation users around the country that displaced traditional supercomputers, monolithic supercomputers, and gave a improved performance per dollar for being able to solve some of the most capable science problems. And today it's ubiquitous. Just about every supercomputer today uses Linux and is some derivative of this machine. In fact, today and for the last 5+ years, all of the top 500 supercomputers in the world have been based on Linux. So this is a quote from the very well-known Steve Wallach, computer architect and winner of the Seymour Cray Computer Engineering Award, commenting on this achievement. So as I mentioned, I'm at the New Jersey Institute of Technology. That is a public university, a top R1 school in New Jersey, continuing to climb the ranks of the US News and World Report and other rankings. I both direct the Institute for Data Science that I show here, but I also launched the Department of Data Science in fall of 2021. We have a bachelor's, a master's, and a PhD degree program in data science. My institute, which encompasses the research, aims to solve real-world challenges. We have about 40 faculty in our current centers, and they include a center for big data that's focused on big data analytics systems and tools and cyber infrastructure, a cybersecurity research center that focuses on practical encryption, privacy technologies, and information assurance, a medical informatics center that works with NIH and the National Cancer Institute, a group focused on fintech, which is research for financial services in the insurance industry, and then a brand new center that we've launched in machine learning and AI, where we house some of our industrial partnerships and focus on real-world technologies using machine learning and AI. So I'm very proud to be running this center this institute going on 4 years, focusing on some of the problems that really matter in the real world, including urban sustainability, healthcare analytics, how to have trustworthy, free, and fair elections, insider threat detection, utility infrastructure protection, cyber attack defense and giving attribution to major attacks, and also disease outbreak and epidemic monitoring that we have seen as very useful at having come through the COVID-19 pandemic. So these real world problems are really what motivates the research inside of our institute and what our faculty and our students engage in. I like to think about data in terms of these two axes. And on the x-axis, I have objects within the data from known objects on the left to unknown objects on the right, and patterns from known patterns on the bottom to unknown patterns on the top. So if I put problems into these four quadrants, for instance, the lower left quadrant, where I have known patterns and known objects, this is where relational databases in the 1980s did quite well. For instance, we may run a store, we have our items that we're selling in the store and descriptions of those items. May have records of our customers, and then also we have records or tables related to the items that a particular customer may purchase. And through that relational database, we may be able to ask a lot of questions about what are the most popular items bought and by whom. On the off diagonals, I have, for instance, on the upper left, known objects but unknown patterns. And an example of this may be a cybersecurity problem where a chief information security officer notices one individual in a company that continues to trigger some tripwires set around the company. And they're trying to find out, for instance, this user accessed files they didn't have permissions for. They may have visited websites that they should not be looking at. They may have tried to access storage and so on. And what the CISO or Chief Information Security Officer wants to do is look at the neighborhood around this known person and find out, are they colluding with another employee? Was this part of a pattern, and so on? And vertical databases of the 1990s have been very helpful for being able to solve these types of problems. Or the one on the lower right, where I have the problem of subgraph isomorphism. This is a image where I have a template of a pattern that's inset. So this is a known pattern. Then I have observed activity where I'm trying to find an exact copy of that pattern or something close to it. Now, the quadrant that really excites me is this upper right quadrant, or sometimes referred to as the fourth quadrant of unknown unknowns. And here's typically where I have data, and I don't know what patterns exist in the data. I don't know what objects exist in the data. And what I want to do is remove surprise and try to understand what is happening in this unknown sea of data. And in many problems in application spaces, this unknowns, this data may be massive, it may be huge. And what I want to do is create tools so that analysts can go through this information and be able to better understand what's there. And the heart of my talk will be trying to understand what is in this fourth quadrant of data. Now, I segue to graph data science because often in that fourth quadrant, we have relationships between items. And once I have relationships, they induce a graph where the relationships form edges and they act on objects that form vertices in the graph. And so I start to take those unknown unknowns for these real world challenges and build these very large, what I call here exascale streaming graphs. And what I mean by streaming is that the graphs and information that I receive is constantly flowing. I constantly have new data that I want to understand. So this paradigm works across a variety of different problem domains. For instance, in healthcare, trying to understand the epidemics and pandemics that we're faced with, or in massive social networks, trying to understand how communities form, what their intentions are, even transportation and evacuation during emergencies. For intelligence, business analytics, and trying to understand what's happening within a company, trying to detect anomalies, security problems, all relate to exascale streaming graphs. And many of these others, the electric power grid, power is important for our communication networks, transportation, energy, even our water and our food supply that are needed to sustain life. So it's very important to have a resilient power grid, and we can use these graphs to try to detect attacks and failures on these grids. All the way up to modeling and simulation, we may want to perform full-scale economic, social, political simulations on entire countries and nations to try to understand policy impacts or particular decisions that are made. So all of these require predicting, influencing change in real time and at enormous scales. So we've aimed to develop open source tools that can help analysts on these types of massive graph analytic problems. But when I talk about graphs, graphs come in many shapes and forms. And the sources could be from simulations that get run on computers. It could be from experimental devices, the internet itself, from the massive sensors that are deployed everywhere, scientific applications. So we know data comes from all sorts of places, and we have new challenges in terms of the data sizes, the heterogeneity, uncertainty within the data that we collect, the data quality, and more. So this is quite a challenge to come up with analytics. But let me tell you about 3 different areas that I depict on this slide. For instance, in astrophysics, we may be looking for quasars, and we have these huge digital sky surveys, and we may be looking for outlier detection between 2 images that would tell us that there may be a quasar, and we only have minutes to turn a radio telescope to look in that direction to try to observe the astrophysics activity. But we're challenged. These are some of the largest data sets that exist today. There's many temporal variations when we look out into the sky, and the graph problems that we may be trying to solve look like clustering or matching between images. In bioinformatics, we may be trying to identify drug target proteins, and we'll build graphs out of the protein-protein interaction networks, but we're challenged by the heterogeneity from data coming from different laboratories and the quality within our data sets. And then the graph problem that we may be trying to solve could be something like centrality, trying to find the most important proteins within these networks, or clustering the proteins that we have. On the very right-hand side is an example from social informatics, where maybe we're trying to discover emergent communities or model the spread of information or disinformation across social networks. And our challenges are that we may need new analytic routines that can try to solve the analytic that we're looking for. There's a lot of uncertainty in the data, what we're able to see and not see. And then the graph problems may look like clustering of vertices together, shortest paths in the graph, flows in the graph, and so on. So not every graph application is the same, and we really have to look at the types of applications we're trying to solve to apply the right graph analytics and also the right graph algorithms to solve it. So for instance, I mentioned the electric power grid. This is a graph that shows some of the major grid points in the United States. And we know that a blackout will lead to real catastrophes, whether it's knocking out heating or cooling. It leads to fatalities, loss of manufacturing, and real devastation when we lose parts of this power grid. Here's an example from network analysis for intelligence and surveillance. On the top graph is a graph that represents the hijackers on the September 11th terrorist attack on the United States. And it was argued that if we could have run an analytic such as between-us centrality, we would have been able to pick out the masterminds and who was on each of the planes that flew that day. On the bottom is another graph that's taken from communications of the ACM, and this is a graph that I showed on a previous slide. where we may be looking for a pattern. In this case, here are two people that live together. One is renting a truck, the other is purchasing fertilizer, and they're observing a building or a factory. And that may be a pattern of building a homemade bomb that we may try to look for in some observed data. So this is also called exact or approximate graph matching, as well as subgraph isomorphism. So all of these are very important graph analytics that we aim to solve. And even though I talk about social networks, sometimes we can apply those social network algorithms to other domains. This is a snapshot of some previous work I did with Kamesh Maduri, now a professor at Penn State, where we looked at the human proteome and applied a graph analytic of between centrality on the roughly 44,000 protein interactions that were known at the time. And what I have here is the quote unquote answer that's plotted. On the x-axis, I have the degree of each protein on a log scale. So what degree means is how many other proteins that one interacts with. So every black dot is a protein. The ones towards the left have very little interactions. The ones on the far right interact with a lot of other proteins. And then on the x-axis, I have their normalized between centrality score on a on the on the y-axis, and this is a log scale. So proteins on the very bottom have a low centrality, meaning they may not be that important in the network, and proteins at the very top have a high between centrality. So it turns out the protein that has the highest between centrality is not the most interactive in the network. So this is like trying to find a needle in a haystack, but it's a protein that's been implicated in a breast cancer. So these are the types of discoveries that we can make, finding needles in haystacks by doing this type of graph analytics. Now, we have moved from really using traditional high-performance computers to analyze graphs to more what I have on the right-hand side, streaming analytics. I think of data as constantly in motion, and many problems or how these were done in the past is that we would load information into a big supercomputer, and then we would do an analytic. And this is really great when something bad has already happened. And what we want to do is forensic analysis. For instance, there was potentially a breach at a company. We collect all of our system logs together. We analyze them to figure out how the breach occurred and what was damaged, what was taken. And that's what we do after something egregious has happened. But where we have to get to is on the right-hand side, which is really the emerging area of predictive analytics, where we're trying to understand the data as it's coming to prevent these egregious events from happening. And that's what we've been focused on, trying to create new streaming analytics at scale that can update the graph in near real time and run analytics concurrently to try to solve these types of problems. So for example, we were the first group that analyzed all public tweets in Twitter, and as of this week now at X. So this is the old Twitter, if you will, where we took in all of the tweets in fall 2009, and we piped them into a big supercomputer, and we ran graph analytics on the followers and followees. And our ad hoc results, I'll just give you some of them from this paper, where we looked at an emerging spread of a virus, H1N1, an influenza virus. And it was thought to have double-digit mortality until the virus actually came, and it turned out to be not as lethal as expected. But we want to understand where were people getting their news from. And so on the left-hand side, we ran between centrality analytics to pick out the most influential Twitter handles. And the top 15 are shown here on the slide. And what we liked was that we were able to get, for instance, the US government, the official Twitter handles like number 1, CDC flu, number 4, flu.gov, number 12 and 13, CDC emergency, and CDC eHealth. So it's great to see that these were influential news sources. And we also saw commercial media like number 5, the New York Times, number 8, CNN, number 11, Time Magazine, and so on. And so that was great that those were really having influence in where people were getting their news. But we also had some surprises. And again, this is like being able to tune your radio in to a news source during a breaking event. And you would never think to turn to the third top Twitter handle on this list, Official PAX. It turned out Official PAX was the handle of a gamers group called Penny Arcade, mostly adolescent white males who at this time were gathering in Seattle, Washington, in the United States, about the time of the outbreak of H1N1 in fall of 2009. And they were the first group to catch N1N1 amongst each other and started tweeting about the symptoms and how they were doing. And this led to great information that wasn't available from any other source to understand the disease and how it spread. So this is the power and capability of graph analytics. At New Jersey Institute of Technology, I'm very excited to have support from the National Science Foundation to try to democratize supercomputing and interactive data science at these massive scales. So we've been hard at work for the last several years building out an infrastructure that I want to tell you about today that is now getting quite a lot of use. And it's an open source project, and I'll tell you a little bit more about it next. Often we're trying to solve problems. For instance, we may have a medical problem where we're faced with trying to find patterns within clinical patient records. And our system that we're building out is called Arachne, the Greek word for spider. And what we may do in our large-scale graph analytics is ingest these electronic health records into a system and then run graph analytics to understand patients and the communities that they sit in. So this is one use of the work that we're building out. Another may be for trying to model pandemic spread. So for instance, here's a graph that shows different patients who are infected, exposed, hospitalized, recovered, or unfortunately died in a hospital. And what we're trying to do is understand these patterns between individuals in a population. So there are many different graph analytics that can be used to simulate the spread of pandemics. Centrality that I mentioned earlier finds important vertices in the graph, and also visualizing the spread of the pandemic can be used to check the effects of intervention methods and control strategies. So these data sets can be from millions or even trillions of vertices, very large in size. We also look at, for instance, contact tracing networks for diseases such as COVID, HIV spread, and so on, where we have graphs with millions of edges and vertices that may become extremely large in size. And we want to run graph analytics like K-trust, triangle counting, triangle centrality, and others to be able to try to understand how these viruses spread among individuals. And also looking at population health data analysis. Again, we may be faced with terabytes upon terabytes of tabular data, and our system, Arcuda, which is the base system that we're building on, that's the Greek word for bear, I'll tell you more about, that could build property graphs, and then our graph analytics system, Arachne, could operate on them. And so these are the types of problems that we're focused on, among others. When I talk about this project, I'd like to dedicate the next part of my talk to my colleague and friend, Mike Merrill, who unfortunately passed away early last fall. He was the inspiration for the Arcuda system that I'm going to tell you about, and we'd like to think that we're continuing upon his work. He was a great colleague, and again, I had many discussions with him until he unfortunately passed away, but was very, we agreed that whenever I would talk about Arcuda, I said that I would always mention him. So we had this vision to build a system that has both the productivity of analysts being able to use Python. And Python is the lingua de franca of data scientists. Everyone knows how to program in Python and implement a data science application, often using packages like NumPy and Pandas, NetworkX, and others. And we wanted performance, so we're leveraging a high performance productivity compiler called Chapel from Cray, now HPE Cray. And we've married these two together to give us the best of both worlds. Productivity, so analysts who don't need to know heroic programming, don't need to know how to program in C or assembly, don't need to know how to use supercomputers, can actually write their Python codes, but have it run on a supercomputer in the back end at high performance. So we're making this illusion come true. Here's a sketch of how this Arcuda framework works. We have a user on the very left who's a data scientist who is very comfortable with their Jupyter notebook or the writing Python code. And that is connecting to a Chapel server through ZMQ, zero message queue. And all of the massive data is sitting within that machine, a supercomputer, but it could be a cluster, it could even be a laptop, a shared memory machine. And all of the information is spread across that system. What Arcuda provides are modules for indexing, arithmetic, sorting, IO, and others. And what we've been building out are modules for Arcuda that handle graphs. And we call this subset Arachne. So Arachne is a piece of Arcuda for doing these massive scale graph analytics. Now, the target for this system was really to take analysts who know very little about programming. They can use Jupyter notebooks and in a couple lines of Python code express what they want to run. And we wanted to give them the capabilities of frameworks like NumPy and Pandas, but to be able to run on tens or even hundreds of terabytes and to have it work interactively and at scale, and not have to know all the details of that back end. And this has been realized. We've been building out this system for a couple of years now. All of our code is open source, it's freely available, and we encourage others to pick it up and try it out. It's on GitHub. I have a couple links in the slides here. And we also have some tutorials available if others wish to try to use this new framework. So the major contributions are building out this graph analytic framework called Arachne. That's an extension of Arcuda for productive graph analysis. We're building novel sparse graph data structures and then algorithms on top. So we're leveraging both productivity through Python and that high performance boost of supercomputers backed by Chapel from HPE Cray. And I should mention, all of this is open source, including that Chapel compiler from HPE Cray. So it's a completely open source solution. And the experimental results that we have on real world and synthetic graphs demonstrate that Arachne works on graphs with billions or even trillions of edges. So I encourage you, if you're interested in large scale graph analytics, to give Arachne a try. We scale beyond any enterprise commercial solution out there. So we're very proud about this work. The heart of it is having a data structure for these large scale graphs that sits within the Arcuda framework. So this is the Arachne double index data structure, and it allows us to access a given vertex from an edge ID in constant time, or locating the adjacency list from a given vertex also in constant time. And so there's a few auxiliary arrays, this edge index and this vertex index, that allows us to be able to access our graph either in an edge-centric way or a vertex-centric way, and to load balance the accesses across a distributed memory machine. So this is an improvement over the standard way of representing large sparse graphs in compressed sparse row or CSR format. So this was something that we needed to build out. And we have recently released a new version of Arachne that handles not just simple graphs, but property graphs. So a property graph is a graph, as I have an example on the upper left-hand side, where vertices may have types and edges may have types, and also the edges may be directed. In this example, the top two vertices are colored blue. They're person number 34 and person number 23. And then on the bottom, the green vertex is a vehicle, which is a car number 89. And there could be attributes on those vertices as well. For instance, person 34 is Anne, born in 1990. Person 23 is Dan, born in 1975. And that car on the bottom is a Tesla Model X. The edges also represent relationships. So we have an edge from Anne to Dan that says Anne lives with Dan, and an edge from Dan to Anne that says Dan lives with Anne. So we have edges in both directions. We have Anne driving the Tesla since January 2011. We also have Dan driving the Tesla since 2011, and also another edge of Dan owning the Tesla registered January of 2011. So these are property graphs, and often we may have queries that ask particular questions about graphs that have types on the vertices and edges. And we're now able to handle these property graphs and do a lot of cool analytics within Arachne. So Arachne has a number of modules for reading and processing graphs, and then running a number of the graph analytics using that graph data structure, DI, for the core of representing that graph. And we're also able to run benchmarks across many of the algorithms that we have designed. So to date, we have, in the last 2 years, built out algorithms to run breadth first search. That's where we have a graph and we want to figure out how many steps away is each vertex in that graph from some starting vertex that's given. Connected components returns the set of maximally connected vertices and gives them all a unique ID, and then does that for each component in the graph. Trust analytics uses the notion of triangles to find triangle support for denser objects within the graph called a truss. And we're able to find K-trusses, max trusses, truss decomposition of graphs, and so on. So these are very useful for some analysts who like to think about running truss analytics rather than NP-hard community detection algorithms. This is more a surrogate that runs in polynomial time. Jacquard coefficients gives us Jacquard similarity or Jacquard weights between vertices within the graphs, often a measure of similarity. And we can also count triangles in the graph. This is a circuit also for finding communities where triangle counting is useful in many other analytics like the truss analytics, but also in clustering coefficients. And the next analytic on the slide, triangle centrality, which is a new type of centrality due to Paul Burkhardt a few years ago that returns the highest important vertices based on the triangles centered at that vertex. In our work with Arcuda and Arachne, we've had many papers and novelty in our new implementations of these algorithms. So I won't go through all of the details on this slide, but we've developed some new algorithms in the process and also improved some existing algorithms to get the high performance for these different analytics within Arachne. So for instance, triangle counting, how many triangles are here in this graph of 9 vertices? Well, it's not really a trick question. So here's a triangle 1, 3, 4. Here's another triangle 3, 4, 7, and so on. So there's 5 triangles, and triangle counting is trying to compute how many triangles exist in a given graph. So the triangle count is 5. This is the pseudocode for what we're doing for a very new triangle counting algorithm that we call minimum search. So it's a algorithm implemented in Chapel. I won't go through all of the time or all of the pseudocode here, but we're essentially inspecting edges to create wedges in the graph and then trying to figure out if there's a closing edge to that triangle. So for in this case, we may have threads that are examining the vertices U and V, looking for triangles that are adjacent to U and V. One thread will search and find W1 in V's adjacency list, but it's not adjacent to V, so we don't have to pursue that more. Another thread may be searching for W2. W2 is not adjacent to V, so we don't pursue it anymore. But a third thread may find W3 and find that V is adjacent to it, and then we increment that we found a triangle. So this is just a very high overview of how the algorithm works with optimizations to try to minimize the number of comparisons that need to take place. So our minimum search method does have provably less operations than a naive approach for triangle counting. The list intersection that we do between vertices requires analyzing the entire longer adjacency list against the much shorter one, but we avoid doing such a large computationally intensive search every time, so we're able to reduce the operations. We've also implemented connected components. Here's 1, 2, 3, 4, 5, 6 components where vertices 0, 1, 2, 3 are components, 4, 5, 6, and 7 are a component, and so on. And we're trying to find these quickly in a graph. Often an analyst may be able or may be interested in pulling out the largest component to look at it, or pulling out small components to inspect them, and so on. So our algorithm we have called the fast spreading connected components algorithm with some novelties on how it works. The pseudocode is on the slide here. And again, the implementation is not too many more lines of code than what we have here. What we try to do is keep pointing vertices towards a canonical vertex until our output is each vertex points or has the label of the smallest vertex in its component. And we want to propagate those labels very fast. And that's what our approach does. It looks at the minimum label in a component and keeps propagating them efficiently until all vertices in the component point to the smallest label. So let me give you an example of running some of these algorithms with Arcuda and Arachne within a Jupyter notebook. So I know this may be a little bit hard to see on the screen or to follow along closely, but I can make the slides available. And again, this is copied from the tutorial that we've given that's also available from our GitHub repository. So the first thing we do is connect to an Arcuda server. And then here we're reading in the graph from a file. And for this small example, for the talk here, I loaded in a graph with 10 vertices and 13 edges. And I can add edges to the graph. I can remove edges from the graph. I can also display the graph if it's small enough. And here at the very bottom is an example of displaying the graph through NetworkX. So here's a picture of the graph that I loaded in. And at the bottom, I want to run a query to try to find the vertex with the highest degree. And it happens to be this vertex number 6 that the arrow points to. Also, 8 is a vertex of maximum degree, but the algorithm returned the first one it found. So 6 is the first occurrence. And maybe I want to do a breadth first search from that vertex. So the analyst would then call breadth first search, and here's a graphic of the answer that comes out. So 6 is now the center or root of the breadth first search. And we find all the vertices that are 1 step away, 2 steps away, 3 steps away, and so on. So this is very simple Python code that the analysts had to write, but they can get tremendous performance. Here is an example of graphs that we tested on both real-world graphs and on some synthetic graphs as well. So this gives the number of edges and vertices in each graph, and then the number of connected components, the number of triangles found, the maximum K for K trusses that our algorithms found. And these graphs have all different shapes and sizes. Some are social networks, some are planar graphs, and we ran these on some modern Intel Xeon processors to get the performance results that I want to share with you in the next few slides. These are the results for the real-world graphs using our Arachne framework. On the x-axis is the number of edges in the graph on a log scale, and on the y-axis is the running time of our methods, also on a log scale in seconds. Now, each one of the algorithms we're running is one of the series on this graph. And the the inputs that we're using are the data points. We plot each input based on the number of edges that it has from those real-world graphs. The first thing that you notice is that the slowest thing to run is this blue curve on the very top, and that's graph construction. So it's one of the most time-consuming aspects of our graph analytic framework, but often this is the graph construction to build the graph the first time, and once it's built, then we can run many of the analytics much, much faster. So all of these other series that we see on this plot are the different graph analytics that we're running, breadth first search, connected components, and so on. So we're able to get pretty good performance on these. And then the same with synthetic graphs. We see on this log-log plot of the size of the graph on the x-axis to the running time in seconds. On the y-axis, the blue curve, again, is the graph construction that is going to be time-consuming, but once we're able to build the graph, then we can run the analytics and multiple analytics that analysts typically would like to do very, very fast. We've been improving in the last year. We've focused on performance and continue to push the envelope on performance. So this slide shows that we've been able to speed up due to new data structures, some of the running times on about a factor of 2, 50% improvement with some of the new data structure enhancements that we've been able to produce. So again, we're very excited by the results that we have presented here, that we built an open source framework for democratizing large-scale graph analytics. You can find much more about this work published in the literature. The top paper that is highlighted is a paper from last year's IEEE HPEC conference. And that paper really describes Arachne as the package that I talked to you about today. And then many of the analytics themselves are documented in papers that I've also described on this slide from the last 2 years. So this has been a very productive endeavor. And as I mentioned, the impact has been tremendous. We have approximately 24 users today using Arcuda on a regular basis with the Arachne Graph Analytics, and they're giving us feedback on the performance as they start scaling their problems up to tens or even hundreds of terabytes of data. So we're excited that we've been able to design and develop this high-performance graph analytic framework, and that we're in the process of optimizing our methods continually to perform better. And also we're implementing new novel algorithms. This week, we're integrating some string algorithms, for instance, large LCS, large common subsequence algorithms. We have suffix arrays and other string algorithms now implemented. We also have some improvements to triangle counting. We're working on community detection and machine learning that we hope to roll out by the end of this summer. If you're interested in this area, I encourage you to pick up this brand new book on massive graph analytics from CRC Press and Taylor and Francis Group. I edited this, and I should say I received no royalties. They all go to charity. So this book is about 600 pages, and it has about 21 chapters on large-scale graph analytics, from searches and paths, algorithms for structure, applications, models, frameworks, and software, and covers most of the work being done today at the area of large-scale graph analytics. There's about 85 contributors. In fact, some of the folks on this call may be contributors to the chapters in this book. And I really encourage you to pick up this book if you're interested in learning more. And finally, to conclude, I want to thank my research lab that has contributed to the work here. My research faculty member, Dr. Zihui Du, PhD students who are some of the major contributors to this work. We've had a number of undergraduate research assistants, as well as some high school interns who have contributed to the work that I presented today. So thank you again for your attention, and I would be very glad to answer any questions that you may have. Thank you very much.
I have a question about
Sure.
so on your, I think it was your introduction slide, you had that you directed the cell processor with Sony, Toshiba, and I forgot the other company. I was just wondering how, the only reason I know that is because I remember when I was uh for PlayStation 3, they put that processor in it. And I was just curious about the whole development process of how that went for
So
that processor.
great question. Thanks for noticing that. So I did some pioneering work on the cell broadband engine processor that IBM built for the Sony Toshiba IBM partnership and was in the Sony PlayStation 3 that you mentioned. I don't have any slides on that chip within this talk, but I led the first Sony Toshiba IBM Center of Competence for the cell processor around 2006 to 2009. So what was incredible was that those with PlayStation 3s could boot their PlayStation with Linux and run Linux applications and even build clusters of PS3s for high performance computing. Now, that cell processor that I worked on also accelerated the first petascale supercomputer in the world that was at Los Alamos National Lab, also called Roadrunner, which was launched in 2009 and broke the petascale barrier accelerated by that graphics processor. So those accelerators were similar to what we see today with NVIDIA GPUs accelerating much of our machine learning workloads for training neural networks or accelerating scientific computing codes. As I mentioned in my talk, most of the high performance computers today are using Linux, but many are accelerated by GPUs, for instance, from NVIDIA and others. So the accelerators have really stood the test of time, and we'll continue to see accelerators such as these that are built for graphics and gaming, but used for scientific computing and other workloads.
Thank you for answering that. I remember I was I was either reading something or listening to a podcast, and what you mentioned about in the US military or whatever, some lab used a bunch of the PS3s like put them together to do uh, data processing, as you mentioned.
Correct.
Yeah.
So that was a project at the Rome Air Force Laboratory led by Rich Lindemann, connected together a number of PlayStation 3s to create an inexpensive supercomputer out of them. Just a fantastic project.
Thank you.
You're welcome.
Just as one piece of housekeeping, if you are an IEEE member, please type IEEE into the chat so I have an idea as to how many attendees are IEEE members.
Any other questions from those in the audience? So I've had the pleasure of mentoring quite a number of students and very diverse students through the years. And I had shown some of my current students on the last slide, but I encourage many of you who are doing research to try to include students, both men and women, in your research. That is really quite rewarding to see these young and eager minds engaged in research and lead to really impactful careers in science and technology.
We have time for one or two more questions. So if there are any more questions, I'm going to give this as the final question, the final option for questions tonight.
So I see a question in the chat from Gene Freeman. What about GPUs makes them applicable to graph computations? So that's a great question. In fact, when I started working with GPUs, and in fact, I was a co-PI on NVIDIA's first federal project under the DARPA Ubiquitous High Performance Computing Systems program, the Echelon project from NVIDIA. And at the time, GPUs were really accelerating graphics, but weren't necessarily appropriate for graph analytics. And NVIDIA gave me the challenge to really hold their feet to the fire and understand what architectural features on GPUs are needed to make them really worthy to do these very memory intensive, irregular graph applications. So what NVIDIA has worked on and what we see in GPUs today results from that program. For instance, work sizes can be much smaller, controllers, higher bandwidth, in fact, memories on the GPUs, and many other aspects that give us, for instance, latency tolerance of applications on GPUs. So there's quite a number of innovations in GPUs today that make them really excellent and highly capable for graph analytics. I see a few more questions in the chat and also Josephine's hand raised. Maybe I'll take one question from the chat and then switch to Josephine. So Dr. Julia.
Can you hear me now?
Oh, sorry, Josephine?
Yes, I was just wondering, thank you, very interesting talk from someone at my alma mater. So I was wondering if you had any thoughts on to add about possible frameworks for evaluating the performance of these models that are maybe independent of the method that you're using, like maybe, for example, using a regression analysis and comparing it to, say, like mean error squared or something like that.
So that question probably is a little bit outside the scope of the talk, and to do it justice, I'd probably have to take your question offline, but thank you for asking. I see Dr. Julia Taylor has asked, can you talk more about the potential applications of these data analytic capabilities? So that's a great question. I talked a little bit about applications in my slides, but one area that we're highly focused on is, for instance, nation-scale cyber security. We'd like to be able to understand attacks on networks and be able to give attribution to those attacks. Often that requires understanding terabytes of data that get generated every time network packets traverse through our networks. And that's one area where protecting our organizations is really critical to be able to decide in, say, milliseconds whether or not to let a packet into our network or not. We also mentioned through the slide some of the health-related aspects, and I'm very excited about looking at applying these capabilities towards the Human Connectome project that I have some collaborators leading at Harvard University and Princeton University, where there's now imaging of brains. We're not quite up to a human brain. We have Drosophila or fruit fly, and we're getting to a mouse brain that are just massive graphs where neuroscientists would like to be able to find particular patterns within these real brains. And so that's an area where we're creating subgraph isomorphism or graph matching, template matching. We're trying to solve these problems with our neuroscientist colleagues. We're working with a company, Accenture, in partnership to try to understand, using graph analytics, the security vulnerabilities of open source software and treating open source software as a big graph, for instance, all of the code in GitHub, and trying to understand malicious actors who place malicious code within the software supply chain. How do we protect against that? How do we detect it? And so on. So there's many real world applications that need these massive scale data analytics. And hopefully, Julia, I answered your question about some of those areas. There's another question from Dennis Mancy about which programming languages other than Python are being used for graph analytics. I mentioned Python because Python has many productivity packages that are just easy to use, but you run out of steam when you run out of the capabilities of being able to store things, say, on your laptop or on a cloud node. So once you get above data sets on 100,000 vertices, or you're trying to run a more complicated analytic, they just run out of steam. Or Python, we know, runs, it's easy to write Python code, but it often runs very, very slow versus some natively written code in high performance languages. So other than that, for graph analytics, we see more frameworks being used. Ones like Neo4j is very common, Redis Graph, Janus Graph, Trovaris, and others are some of the frameworks that people often use for graph analytics. But again, not all of those frameworks scale, and we try to build solutions. Once our data scientists get beyond what they can do on a single compute node, they often get stuck, and we're trying to solve that problem. Thanks, Dennis. Comment from Dr. Julia Taylor, cybersecurity really crucial, brain imaging, wow, open source, yes, thanks so much. So thank you for those comments, Julia. Any other questions from our audience? I really enjoyed talking with everyone today, and I hope you're as passionate about graph analytics and pick up this code, Arcuda and Arachne, kick the tires on it and see what it can do for you. I think there's just another final question I see in the chat from Neil Ormos. Do the analytics frameworks mentioned have only Python bindings, or can they be used with other languages? So I mentioned the work that we're doing with Arcuda and with Arachne. They have Python bindings, which is the natural way to call them, but they're sort of native within Chapel, and this is a high productivity and high performance language open source from HPE. So if you're able to pick up Chapel, that's also sort of a native interface for using these frameworks. If there's a need to interface from other languages, we'd be glad for you to speak with us, and we can see about creating interfaces to other languages. Thank you very much for the question.
Thank you, everyone, for attending tonight. Thank you to our speaker for spending the time with us tonight. And I think we had a very exciting topic, again, thank you everyone for joining us. There will be another Careers in Tech Summer Series session next week, and basically almost every week between now and August 31st. So if you saw the emails for tonight, you will probably see additional emails going out over the next several weeks for additional topics. But again, thank you everyone for attending. Have a good night.
Thank you.